Okay, so I've loaded the part into the vise on the bandsaw. I adjusted it so that the plane of the blade, the plane that the blade will cut through, is aligned with the target mark that we placed on the part before we removed it from the lathe. So now we are ready to perform the bandsaw cutting. Okay, and again, the reason we came to the bandsaw instead of cutting the part off using a parting operation on the lathe, one is to show you the versatility of the bandsaw, and two, because the bandsaw is much faster at cutting. It's a lot less accurate, which is why we left extra material. In this case, we're leaving an extra 1/8 of an inch just to be conservative. Okay, so the bandsaw is a lot faster, but yes, it's less accurate. In this case, I'll retract the blade, turn the machine on, bring the blade gently into contact. Once I can hear and feel it cutting properly, I can see some chips coming off it, then I'm going to enable the automatic feed on the bandsaw, just like we saw there's an automatic feed on the lathe. The bandsaw uses a water-based coolant to help flush chips out of the cutting zone and keep the steel blade cooler as it's cutting the workpiece. I turn this up, you can see the coolant a little bit better. And it has a reservoir at the bottom of the machine that captures the coolant, filters it, and then pressurizes it and runs it back through the system. So it's a closed loop coolant system. Okay, we're coming up on the end of the cut. The blade cut all the way through the part, as you can see. I'm going to turn the automatic feed off. I'm going to retract the blade and the carriage. And then turn the machine off. So now we have our workpiece that's been cut off, about 1/8 of an inch long, and we can return to finish this part in the finish the lathe work in the lathe. Now that we've cut off our part on the bandsaw, now that we've cut the extra stock off our part on the bandsaw, we're ready to reload it in the lathe and finish the turning operations. I've wiped off the chuck jaws. I'm going to use the chuck key. We're going to rotate the part 180 degrees and clamp on the shoulder diameter that we just created in the last step. I'll put the part inside the jaws, and I'll actually push the shoulder we created right up against the face of the jaws. Close the jaws, and then use 2 hands to securely tighten the chuck key. I'll return the chuck key to the top of the headstock. And now we need to reload our turning facing tool. So I'm going to remove this chamfering tool. Reload our turning facing tool. Okay. And I want to begin by taking a measurement. However, the surface on the back side of the part, it's very rough coming off the bandsaw. Again, the bandsaw is a quick machine for cutting materials, but it's not very accurate, and the surface finish isn't terribly good. Okay, so to start with, I'm going to touch off on the new surface, the new backside surface of my part. I'm going to set a Z0, and I want to take a light cut across the back face so that I have a good surface to measure against to determine how much material I need to remove to bring the thickness of the remaining part of the wheel hub into tolerance. 3-step check. So I'm going to rotate the part. I can see I've got plenty of clearance between the part and my cutting tool. I'll put the lathe back in high range. I'll turn it on in the forward direction. And now I'll gently bring my tool into contact with the rotating part. I can hear it, I can see the chips coming off, and now I'm going to set that as my Z0 datum. Okay, using the right hand rule, I'm going to move the cutting tool back towards me in the X direction. Okay, back into air. And now I'm going to move over towards the part, just a small amount to make a cut across the face of the part. Okay, I left an extra 1/8 of an inch when I went to the bandsaw. So in this case, if I move over 30 or 40 thousandths, I should have plenty of material remaining. So 30 thousandths. I'm going to put a little oil on the cutting tool. I'm also going to change my feed direction to cross feed. Actually, I'm set on cross feed, but if I engage it, you can see the tool is moving away from the part instead of towards it. So I need to reverse the direction of my automatic feed with this plunger on the lower part of the front apron. Now if I check, I can see that the tool is moving towards the part as I desire. I'm going to come up close to the part and gently touch off the part. So actually cut into the part. And now I'll engage my automatic feed and cut all the way to the center of the part. You can see a very long stringy chip being produced. So sometimes you have to manually stop the feed to break the chips into small pieces so they don't become unyieldy. We'll cut all the way to the center. There we are. I'll move back outside the part. I'll turn the lathe off. I'll wait for it to stop. I'll wipe my part off for the portion where I want to measure it. I'll grab my calipers, check my zero, and I'm going to measure the thickness of this portion of the part. Okay, I get 0.650, 0.651 right in there. The feature is supposed to be half an inch, 0.50 plus or minus 20 thousandths. So if I'm 0.650, we have, again, about 150 thousandths remaining to remove off the part. So what I will do is the same thing I did last time. I'm going to get these chips out of my way using the rag instead of my hands. Okay, you never want to grab the chips by hand with your hands because the chips are also very sharp and they get caught on everything in the cutting zone. Okay, so what I want to do, I've made that cut. I haven't moved the machine in the Z direction, so I'm going to re-zero. I'm going to set that as my new Z0, my new reference. I know we have to cut 150 thousandths off this face. We could do it in 2 passes. Here, physically, I can only, again, the depth of cut, this time it's into the part in the Z direction. The maximum depth of cut is 100 thousandths. So let's start there. Let's move over 0.1 inches in the Z direction. I'll move the tool back away from the part. I'll check, make sure I have clearance between the part and the rotating part and chuck and the cutting tool, and I do. I'll put the machine back in high range, turn it on in the forward direction. I will add a little cutting oil to the tip of the cutting tool. I'll bring the tool in close to the part, gently engaging the part. And now I'm going to engage my automatic feed. You can see with this roughing pass, the chips are big enough where the cutting tool is actually able to break them into small pieces that easily fall down instead of getting tangled on the rotating jaws. So that's another benefit to roughing passes, is that the heat produced and the stresses imparted into the chips often cause the chips to break into smaller pieces. I'll cut all the way to the center. I'll stop. I'll retract in the X direction. You can use the right-hand rule, so I know counterclockwise is going to retract the tool away from the part. I'll turn the lathe off. I'll wipe the part off once again. I'll double check where I am. I expect to be somewhere around 550. Okay, my measurement shows I'm at 0.545. If I rotate it, take a second measurement. 0.544. Okay, so pretty consistent there. So that means if our tolerance is plus or minus 20 thou, 544, I have to cut off at least 24 thousandths more to be within our tolerance band. But I'm going to just try and go right to the middle of the band. It's a nice big band for a lathe with a DRO. With a digital readout, it's plus or minus 20. So I'm just going to try and go right to the nominal size, which would be another cut that is 44 or 45 thousandths in size, in magnitude. So I'm going to move over 45 thousandths. somewhere there. I'll check my clearance. Engage high range. Turn the lathe on in the forward direction. Add a little cutting oil. Okay. I can make my cut. This 45 thousandths, so now we've got to make a judgment call. This 45 thousandths is going to bring the part into tolerance. Okay. The only reason that I would break this up and do 2 passes is if I really wanted to do a finish pass, but you can see on the tailstock camera that the finish that's being left on the part is exceptional. I started with a new cutting tool. Okay, so it has a this tungsten carbide cutting tool has a very easy time cutting the aluminum, and it's leaving a very brilliant finish. So there's no need in this case to break this up into 2 passes. So even though this is larger than our 20 thou finish pass, and I told you that it's good practice to do roughing passes first and then do finish passes, okay, I'm just going to show you that in this case, the tool is capable of taking a larger cut than 20 thousandths and still leaving, hitting the tolerance very closely, very accurately, and leaving a very good surface finish. Okay, so as your materials get tougher, as you start cutting steels and titanium, tougher materials like that, or as your tolerance bands start getting smaller, then you'll benefit more from using that protocol of leaving 1 or 2 finish passes at the end of each of your part features. Okay, so I'm going to turn the machine on in the forward direction. Come in and gently engage the part. Then I'll engage the automatic feed. I'll cut all the way to the spindle center line. There we are. And now I'm going to move away from the part in the Z direction so that I don't smear the nice surface I just produced by backing up across it, essentially backwards, as I move it out in the X. So instead, I'm just going to move in the Z away from the part, and then I'll turn off the lathe. I'll grab my rag, wipe off my part, get my calipers, check my 0, and check my feature. In this case, I get a reading that is somewhere, I don't know if you can see that on the camera, it's somewhere about 0.500 to 0.501. So we're right where we wanted to be. We're right in the middle of our plus or minus 20 thousandths tolerance range. So that feature is definitely good. That's the last turning and facing operation that we need to do on the part. So I'm going to remove our cutting tool. But as I noted before, whenever we make a pass, there's going to be a very sharp edge left on the part. If I look at our part drawing, there's no chamfer called out on this edge, however. Okay, so they just have the sharp edge shown, but the note that says break all edges is going to apply here. So the way that we would break or deburr that edge is to use a file, a hand file. And this is an important method or practice on a lathe, so I want to demonstrate it on camera. Okay, to use a file, we want to take the tool off the machine, as you saw me do. I'm moving the tool post out of the way. I'm going to turn the speed all the way down to the lowest setting. So now if I turn the lathe on, the part's rotating slowly. And what I'm going to do is I'm going to remove that sharp edge using this file. Okay? There's 2 ways to do it. I could file right-handed. So the way the file works, you have a handle and the tip you hold with your opposite hand. So I could file right-handed, or I could file left-handed. If you file right-handed on a lathe, if I demonstrate, you can see to do this, to bring the file into contact with the part, look how close my wrist would be to the rotating chuck jaws. So that would be very dangerous, okay, especially if I broke the rule and I was wearing a bracelet or a watch or any jewelry. Okay, so you never want to file right-handed on a lathe. You always want to file left-handed. So what that means is that I'm going to shift my body over towards the tailstock, and when I do this, I'm going to just gently bring the file into light contact with the rotating part. But you can see when I do so, none of my body is near the rotating chuck jaws. The second reason that we can do this on this machine, that we can do it in our lab, and I want to make sure if you ever do it, you make sure the second step is present, is because we have an emergency stop bar at the bottom of the lathe. I don't know if you can see it on the camera, but if I push it with my foot, you'll see the chuck automatically stop. Okay, so that's a safety that I can use. I can keep one foot on it, and now I can gently and carefully bring the file in close to the rotating part. I'm going to rotate the file to about a 45-degree angle, and I'm just gently going to bring the file into contact, and I'm going to let the machine do the work. I'm not moving the file around, I'm just touching the workpiece lightly. And again, if anything happens, I can just activate the stop switch very easily with my right foot. I'll just bring the file into contact. I'm not putting a lot of force on the file. I'm keeping my weight on my feet, on my CG. I'm not leaning into the machine. Okay, so this is a safe practice, especially when you have the emergency stop bar. Okay, so I think I'm finished. I'll put the file down. The machine's off. I'll wipe the part off with a rag. And just like a sharp knife, you never want to check it with your finger to see if it's sharp or not. You always want, you never want to check it by moving your finger along the sharp edge. Okay, you always want to move your finger perpendicular to the edge, just to make sure that you, in this case, that we removed the sharp edge, and indeed we did. So that's all we need to do with the file. That's the second way to break a sharp edge. You saw how to make a chamfer. I could have used the chamfer tool just as easily. Okay, I like to use each feature just to demonstrate a different aspect of the machine. So this feature is within tolerance. We've deburred the sharp corner. Next, we are on to the center hole that is that is called out on the drawing for this workpiece. As we can see from the part drawing, the hole through the center of our workpiece measures 0.3135 to 0.3145 in size. Before we manufacture this feature, we need to discuss common hole making methods so we can select one that's appropriate for our given tolerance band. The first and simplest method would be to use a drill bit of size .3135 or 3140 to drill the hole directly through the center of the workpiece. Although this would be the quickest of the three methods, it would also be the lowest quality. The resulting accuracy of both the hole location and the hole size would fall somewhere in the range of plus or minus 5/1000ths of an inch. The second method of hole making uses a center or spotting drill to begin the hole and increases its size in quarter-inch increments until the final size is reached. As shown on the accompanying slide, a center drill has flutes that are much shorter and a shank that is much larger than a comparable size drill bit. This results in a tool whose bending stiffness is over 8 times greater than a comparable size regular drill bit. The stiffer center drill increases the locational accuracy of the hole, and the use of multiple drill bits to reach the final hole size allows the last drill to essentially take a finish pass, which reduces the cutting forces and increases the accuracy of the final hole size. As seen in the table, the resulting accuracy for this method of hole making is in the range of plus or minus 2.5 of an inch, or roughly 50% more accurate than just using one drill bit of the final hole size to create the feature. The third and final common method of hole making uses the same technique as the second, in conjunction with a dedicated finishing tool called a reamer. A reamer is a dedicated finishing tool that holds a higher tolerance than a drill bit. Physically, a reamer is different than a drill bit because it has a flat tip with a chamfer, 4 or more straight flutes that are much shorter than a comparable sized drill bit, and it produces a smoother finish and a more accurately sized hole. As seen in the table, The proper use of a reamer can increase the dimensional accuracy of a hole to within plus or minus half a thousandth of an inch, or roughly 80% better than using multiple drill bits alone, as in the second method of hole making. The downsides to using a reamer are the increased tooling cost, as well as the increased time to use one additional tool in the manufacturing sequence. Taking one more look at the detail drawing for our workpiece, we can see the tight tolerance for the center hole dictates that we must use the third method of hole making to produce this feature. Now that we've discussed the cutting tool sequence to produce this precision center hole in our workpiece, let's go through the sequence on the lathe. The first thing we need to do is to install the drill chuck into the tailstock quill, which is very easy. It just slides in and locks into place with friction. It has a taper and a little tang that provides positive mechanical engagement. So now we have a little 3-jaw chuck in the tailstock that will open and close and allow us to clamp different size drills or reamers. We're going to start with the center drill. We talked about this. It is very short and much larger in diameter than a typical drill of similar size. So it's going to be very rigid, very stiff. It's going to produce the initial hole. It's going to start the initial hole exactly on the center line, in this case on the center line of the part. So I will install this drill, the center drill, in the drill chuck, tighten it by hand. It has a big knurl on it, so all it requires is hand force, hand tightening torque, and it will hold the tool securely. I'm going to bring the cutting tool up to our part. I will lock the tailstock body. I will check and make sure that I have clearance. I can see that I do. I have clearance. I'm in high range. I'll turn the machine on in the forward direction. I'll adjust my speed. Again, back to about 400 RPM for the sake of our audio quality during these demos. I will add a little oil to the tip of the drill, since that's the only part that really does any work. And now I'll use the handle on the back end of the tailstock body to slowly advance the cutting tool into contact with the rotating workpiece, and you can see the chips coming off the part. So I drill a little bit and then I back out. I drill a little bit and then I back out. You can see very well that this reversing or pecking motion, as it's called, it helps break the chips into small pieces that can more easily evacuate out of the cutting zone. And this practice is especially beneficial as we start to make deeper holes. Okay? So I'm finished with the first tool. You can see that it created a little crater directly on the center line of the part. If I wipe it off, we can see the crater. I can release the tailstock clamp, bring the tailstock back, using the rag to hold the drill. I can remove the center drill from the chuck, and I can load my 1/4-inch drill bit. Okay, a note for the camera. Drill bits are not sharp on the sides, so if I pick up a drill bit off the counter, okay, I don't have to use the rag, but when they come out of the machine, one, they're covered in chips, and the chips can be sharp, but two, they can also be very hot. So anytime I'm removing drills from the lathe, you'll always see me use a rag, but when I'm installing them, if they're clean, then I don't have to use a rag, but it's just nice practice. So I'll install the drill and tighten it. Actually, use 2 hands. I'll bring the tailstock back up close to my part. Retract the quill a little bit because the center drill is much shorter, so I had to extend it out farther for that tool. I'll lock the tailstock body in place. I will turn the lathe on in the forward direction. Apply some cutting oil to the tip of the drill bit. And gently bring the drill bit into contact with the part. We can see the chips being produced. I will start my pecking motion. The goal is to see the chips easily evacuating through the flutes on the drill bit. Okay, so as I drill, you can see the chips pushing the rest of the chips out. Okay? And when I start to feel more resistance on the hand wheel, I'm going to retract the drill all the way out of the workpiece. I'm going to use the rag to wipe off the chips out of the flutes and put a little more oil on the tip of the cutting, on the cutting tip of the drill. Now I'll re-enter the workpiece and I'll gently re-engage where I left off. Right there. I can see the chips coming back out. I'll continue with my pecking motion. Okay, and the pecks are usually about the size of the radius of the drill bit. Okay, so what that means, this drill bit is about 1/4 inch in diameter. So I'm drilling about 1/8 of an inch, and then I'm pecking. 1/8 of an inch, and then I'm pecking. And whenever I feel more resistance, that means that the chips are starting to clog in the flutes. I need to retract the drill. You can see how the flutes were pretty full. I'll retract the drill bit, and I'll use the rag or the compressed air to wipe off the chips. Got an extra chip right there, so I'll knock it off with the oil bottle, reapply oil to the tip of the drill. I'll re-enter the hole, gently re-engage the bottom of the hole where I left off. There we go. And then we'll soon see the chips coming back out. Okay? I continue the pecking motion. Now I can feel a drop in resistance. And from my perspective, I can see the drill advanced all the way through the rotating workpiece. Okay, so we're all the way through the part. I can retract it now. I can release the tailstock clamp, slide the tailstock back out of the way, using a rag. Okay. I can clean the drill off. I'll shut it off, safely reach in there, grab the drill bit, release it from the drill chuck. I'll wipe it off, and I will grab our next drill in sequence, which this one should be a .297. We'll load this into the drill chuck. And now that we have a hole all the way through the workpiece, this drill will advance much more rapidly. So come back up close to the part, lock the tailstock, reapply oil, turn the machine back on in the forward direction, and bring this drill gently into contact with the rotating workpiece. Here are our chips. You can see the chips are pretty small because this is not too much larger than the previously drilled 1/4 inch hole. Okay, that's all the way through the workpiece. I'll retract it, turn the lathe off, move the tailstock back, grab the drill, release it, wipe it off, return it, and then the fourth tool in our sequence, and the fourth and final, is the reamer. So this is the reamer. It is .3135 inches in size, .3135. If I load it, we're going to use it the same way that we used the last drill bit. We're going to put oil on it. We'll bring it up close to our part. We'll lock the tailstock clamp We'll clamp the tailstock body so it doesn't slide now. I can see I've got clearance. I'll turn the machine on. And this reamer, it's removing so little material, and really all reamers work this way because by definition, all reamers are finish tools, but the reamer is removing so little material that we don't need to peck. So we can just gently engage the workpiece. We can see the chips being produced. We can feed right through nice and slowly all the way through our workpiece. I'll check visually. I can see chips coming out the back side of the part. And now I can see the reamer coming out the back side of the part, indicating we're all the way through. So I can retract the reamer. I can turn the lathe off. Retract the tailstock body. I can grab the reamer and release it from the tailstock. Wipe it off. And return it. If I wipe off our part, we can see that we have a hole through the center. And if we used a gauge to measure it, we would see that that hole is very close to the size that's listed on the reamer. So the reamer says 0.3135 inches. If we measured that, we would see that that hole is within 2 or 3 tenths of a thousandth. So plus or minus 0.0002 or 0.0003 inches. So a reamer is very accurate. It's more accurate than a drill bit. That's why you would use a reamer. It's going to give you a more accurately sized hole, which is what we want for this feature, because the idea is that this would fit on the precision shaft of an expensive electric motor, and we want to have an exact fit that is close to the shaft size, so a very close clearance fit, but not small enough that it could ever be an interference fit and require the installer to have to force the two together, which would damage the expensive electric motor. Okay, in this case, we've faced off the back side. We brought the right side of our wheel hub down to the half-inch dimension within the plus or minus 20th thou tolerance. We created the center hole, the precision center hole through the workpiece. So we have done everything that we can that involves lathe work on this part. The rest of the features on our part drawing include some holes on the face of this surface, which we're going to do on the milling machine, and some holes, some radial holes on the side of the part for set screws, okay, so that this hub could be used on a shaft that has a D on it for positive mechanical engagement. And those screw holes will also be produced on the milling machine. So we're finished here. I want to remove the workpiece. To do so, I'm going to put the lathe in neutral for safety. And now I can easily rotate the chuck to find the chuck key pinion gear, or chuck key pinion. I can engage that with the chuck key, with the chuck wrench. Yes, the chuck key. Loosen the chuck. I can grab the part, remove it, return the chuck key to the top of the headstock, and we are finished with all of our lathe work.